Hello students, in the last class we were discussing about backface removal. Now we'll see one more algorithm, that is a Z-buffer algorithm. This Z-buffer algorithm is the most widely used algorithm for hidden surface removal. We already know what is nothing but hidden surface removal. That is, when we try to display multiple polygon on an output screen, sometimes some of the polygon may be hidden behind another, or some of the polygons may overlap. In such a case, a part of a polygon or a complete polygon may not be visible to a user. If a polygon or part of a polygon is not visible to a user, then it is not required to process that polygon. If we process that polygon, it is just a waste of graphic system time. So removal of part of a polygon or complete polygon which is not visible to a user from processing is known as hidden surface removal. Z-buffer algorithm is the most widely used algorithm for hidden surface removal. It has the advantages like it is easy to implement in both hardware and software. It is compatible with all graphics pipeline architecture. This algorithm is based on image space approach. We already know what is nothing but image space approach and what is nothing but object space approach. Then to understand Z-buffer algorithm, we have considered a diagram over here. In this, to understand Z-buffer algorithm, we are considering rendering of a polygon or displaying a polygon in three-dimensional system. So in the diagram, we have specified all three coordinates, that is x, y and z coordinate system. Then whatever the grid we are able to observe, that is nothing but a frame buffer. When we are drawing the output or when we are displaying the output in three-dimensional system, then we will be having two buffers. One is known as color buffer, the other one is known as a depth buffer. The color buffer will store the information regarding color of a particular primitive or a polygon. Depth buffer will store the depth information or z coordinate value of a particular entity or a polygon. And then the color buffer and frame buffer will be having same size and they are equal to the number of pixels which are there in a display screen. Even display screen will also have some number of pixels. The same number of pixels will be there in a color buffer and a depth buffer. So the size of display screen, color buffer and depth buffer will be same in number of pixels. Then to understand how Z-buffer algorithm works, here we have considered two polygons to display on output screen. One is triangle, the other one is a rectangle. Before start with the algorithm, we need to initialize the color buffer with the background color and depth buffer with the maximum Z coordinate value. The basic requirement in Z-buffer algorithm is the color buffer need to be initialized with a background color, the depth buffer need to be initialized with the maximum Z coordinate value. Once the initialization is done, we need to start Z-buffer algorithm. Then what we are doing in this Z-buffer algorithm is, whenever we have two polygons to display on an output screen, we need to update the corresponding pixels in a frame buffer. So whenever the pixels get stored in a frame buffer, those pixels will get displayed on an output screen, so we are able to observe the output. Now we need to store the information regarding triangle and rectangle in the pixels of a frame buffer. That is why we are using Z-buffer algorithm. If we are displaying only a single polygon, then it's not required to use Z-buffer algorithm because nothing will be hidden behind another polygon. Because we have two polygons over here, we are using a Z-buffer algorithm to remove the polygon which is hidden behind. Now to check whether one polygon is behind the other, what we are supposed to do is, we need to generate a ray from center of projection through every pixel towards the polygon. So center of projection is nothing but center of a camera or from a viewer. So from a center of projection we need to generate a ray through every pixel towards the polygon. Whenever the ray intersects with the first polygon, the first polygon may be either the triangle or the rectangle depending on the order they have present. So whenever the ray intersect with the polygon, we need to update the color of the polygon in the color buffer and depth of the polygon in the depth buffer. Depth of the polygon is nothing but the distance between the polygon and the center of projection or its Z coordinate value. Whenever the ray intersect with the polygon, we need to update the color of the polygon in the color buffer, that is in the corresponding pixel, and then we need to update depth of the polygon in the corresponding pixel of depth buffer. While updating the depth value, we need to check whether depth value of a polygon is smaller than the depth value already present in a depth buffer. As we know, the depth buffer is initialized with the maximum z coordinate value. So whenever we are trying to update the z coordinate value of a polygon, obviously it will be lesser than maximum z coordinate value, so we can update. Whenever we are updating, the condition we need to check is whether the new z coordinate value what we are updating, that should be lesser than the z coordinate value present in the corresponding pixel of a depth buffer. In such a case, we are supposed to update, otherwise we should not update. Now, as per this diagram, the ray intersect with triangle first, so the color of the triangle will get updated in the pixel of a color buffer, and the depth of the triangle will get updated in the pixel of depth buffer. After that, we'll repeat the same process again for a rectangle. Now we'll allow the ray to intersect with the rectangle also. Whenever it intersect with a rectangle, we will update the depth buffer once again. When we try to update the depth of a rectangle in the pixel of a depth buffer, now the pixel in the depth buffer already contain the depth value of a triangle. Now we are trying to update the depth value of a rectangle, but the depth value of a rectangle is greater than the depth value of a triangle, because from the center of projection the rectangle is far compared to a triangle, because the triangle is nearer to the center of projection or to a viewer, but the rectangle is far away. So whenever we are trying to update the z coordinate value of a rectangle in a pixel, we are not able to update because the pixel already contain smaller z coordinate value, that is of a triangle. With this, what we can understand is whenever we have a multiple polygons, whichever the nearer polygon the ray intersect with, that information need to be updated both in the color buffer and in the depth buffer, because that particular polygon will be visible to a user through that pixel and not the faraway polygon. That faraway polygon will be hidden from the polygon which is present nearer. So this is how we will find out which polygon will be displayed through a particular pixel and which will not be displayed. By using this, we can avoid the further processing of a rectangle through this pixel. This is known as Z buffer algorithm. This is what I had explained till now. That is just a theory. You can go through, and I have explained the complete thing by looking at the diagram itself. Then the next algorithm what we can use for hidden surface removal is depth sort and painter's algorithm. This algorithm is based on object space approach, where depth sort is a variant of painter's algorithm. We will use depth sorting when we implement painter's algorithm. Now to understand painter's algorithm, here we are considering a scenario where a viewer is looking at two objects as shown in the figure A. A viewer is looking at two objects now. One is a triangle, the other one is a rectangle. Whenever the viewer look at these two objects, the object will look to a viewer as shown in diagram B. Now when we try to render these two objects on an output screen, there are two options which are available. The first option is, that is, whenever a viewer looking at these two objects, we are not able to observe both the object completely because part of B is hidden behind A. That is how those two objects will be looking to a viewer. Without using painter's algorithm, if we try to display these polygons on an output screen, then there are two options. The first option is, we can calculate how much part of a polygon B is visible to a user, and then we can display that polygon, and remaining complete part of A need to be displayed. To calculate which part of a polygon B will be displayed on an output screen, we need to perform some of the calculations. That is the first option what we have. The second option is, we need to completely display the polygon B first, and then we need to display the polygon A, so some part of the polygon B will be hidden behind. That is the second option. But instead of using these two options, we have a algorithm for that is known as painter's algorithm to display these polygons on an output screen. In a painter's algorithm, the first step we need to do is to sort all the polygons what we need to display depending on their z coordinate value. We need to sort all the polygons in the increasing order of their z coordinate value. That means whichever polygon is having a smaller z coordinate value, that will come first. Which polygon will be having a maximum z coordinate value, that will go to the last. So in the increasing order of their z coordinate value, we need to arrange all the polygons which we want to display. Now in a diagram, we have considered totally 5 polygons, and we have arranged them in the increasing order of their z coordinate value. So when we observe, A is having maximum z coordinate value and B is having lowest z coordinate value, and in between we have E, D and C. So this is the first step we need to perform in the painter's algorithm. The second step is whichever polygon will be having maximum z coordinate value, that we need to render first. That means with respect to the polygon which is having a maximum z coordinate value, we need to update the pixels of that polygon first in a frame buffer. So with respect to our example, A is having a maximum z coordinate value compared to B, E, D and C. So we need to update the pixels of polygon A in the frame buffer first. Once we update the pixels of polygon A, we need to update the pixels of polygon C, because C is having maximum z coordinate value compared to D, E and B. After C, we need to update the pixels of polygon D in the frame buffer, followed by E, and at last B, because B is having the smallest z coordinate value compared to all other polygons. This is the procedure what will follow in painter's algorithm. The first step is we need to sort or arrange all the polygons in the increasing order of the z coordinate value. Because we will sort the polygon in the increasing order of z coordinate value, because of that reason the name also given for this algorithm is a depth sort. Once we arrange all the polygons, the polygon which is having highest z coordinate value will get rendered first into a frame buffer, followed by the next lowest z coordinate value, and so on till the last one. When we do this, at some time we may get a situation like whenever two polygons are having same z coordinate value, then what we are supposed to do? Whenever we have two polygons which are having same z coordinate value, in such a case we need to compare their x and y coordinate values. If the x and y coordinate value are different for those two polygons, then we can render them easily. One will come behind and the other one will go back. But even if x and y coordinate will also overlap, then we need to perform some of the calculations to display them. That is beyond the scope of painter's algorithm. Painter's algorithm deals with the polygons which are having different z coordinate value, but whenever the z coordinate values are same, in such case you are supposed to compare x and y coordinate values. This is regarding painter's algorithm. Then the next one is anti-aliasing. Anti-aliasing is nothing but sometimes whenever we display line segments or an edges of a polygon, sometimes they look jagged. Jagged is nothing but line segment will not look smoothly. There will be some disturbances in that. It may look like a staircase symbol. That means line segment will not look smoother. So these errors or problems are nothing but aliasing error. The reason for these aliasing errors are, there are three reasons for that. First one is, when you consider any computer system or a graphic system, we will be having a fixed number of pixels. The number of pixels present in a system is fixed. We cannot increase the number of pixels or decrease the number of pixels. Whatever the pixels we have already, using them we can display any object on a screen. That is the first problem. Second problem is, the location of a pixel is fixed. We cannot move a pixel from one position to another position. The only thing we can do is we can fill the information of a particular pixel in that memory area, but we cannot move them. The third problem or the third reason for aliasing error is, the shape and size of a pixel is fixed. We cannot change the size of a pixel and we cannot change the shape of a pixel. Because of these reasons, the line segments and the edges of a polygon will look jagged. The solution for this problem is anti-aliasing. In the anti-aliasing, what is the solution we are providing is, as you know, when we display a line segment, the line segment will be having a length but it is not having a width. Because it doesn't have a proper width, we are facing this aliasing errors. That is, the line segments are not displaying smoothly. Because of that reason, in an anti-aliasing concept, what we are doing is, we will add one pixel width or 1 unit width to a line segment when we update the pixel information of a line segment. So whenever you update the pixels of a line segment in a frame buffer along with the length, we will add 1 unit width to a line segment. Because the line segment is having 1 unit width, whenever it get display on an output screen or whenever it get rendered onto a frame buffer, it will look smoother and without any jag and it is not jagged. So this solution is nothing but anti-aliasing. So with this, we have completed 5th module of your syllabus, and from the next video or from the next session, we will start with the 4th module. In your regular classes, that is before this lockdown, we have completed 3 modules, and in this video and one online class, we have completed 5th module, and then we are left out with 4th module that will start from the next video or from the next session. If you have any doubt in this 5th module, you can text me or you can call me and ask so that I can reply. And you are supposed to practice all the lab set program which I had shared, and you haven't practiced those lab set programs in your regular lab. For that we didn't get time, and holidays are announced after that, so I had shared all the lab set programs in your group. Just practice them, check the output, and in that if you have any doubts, that also you can ask me.